Good morning, everyone. Welcome to IME 470. Today is April the 22nd, and let's continue our topic in minimum spanning tree. And first of all, let me stop the video and share my screen here. And annotate here. The bar is gonna be here. Let me change the color to be blue color. And then the spotlight here. Okay. So in the last class, we mentioned the Prim's algorithm. Okay. In the beginning, let's have a very brief review about it. So in the Prim's algorithm, we gradually adding nodes to P and also put the edges to MST. Okay. And first, we randomly select one node to start. And then what we're going to do is that we're going to find the minimum weight such that one node is in P set and the other node is in V minus P set. And we're going to repeat it until all nodes are added to P. And then I'm done. And in this case, the MST will store the minimum spanning tree. Okay, and we show that an example here. So we randomly start from here and we choose the minimum weight, which is this one. And then now my P is 1 to 2, and then we choose the minimum one such that one node is in P and the other node is not in P, so that we have this or this. And in the slide here, I chose this one. And the next time I choose this one, okay? And then finally, I have either this or this, and clearly this weight is smaller, so I choose this. And hence, I got my minimum spanning tree, which is like this way. And also, we had an exercise about this one. Okay, I remember Patrick. Is Patrick here? No? Okay, I remember Patrick did it correctly. Okay, so in today's lecture, first, I will introduce another algorithm to also find the minimum spanning tree. The name is Kruskal's algorithm. So the basic idea is that we're going to gradually adding minimum weighted edges from E to set K and avoiding cycles. Here, K is going to be the edge set because Kruskal, so we use K, and the previous one because it's prim, so we use P. That's the reason. And the K will store edges. And finally, it's going to store the minimum spanning tree. And the thing is here, we're going to find the best edge without any cycling. So in the initialization, I set K, which means selected edges to be empty set, and I set U equal to E, the whole the total edge set. And step number one is the optimality test that if K already includes all nodes and gives a connected subgraph. By the way, here, it's not strict if we say K includes all nodes, because after all, K is an edge set, But here, by writing K includes all nodes, what I mean is that all nodes are already connected, by this kind of edges. If that is the case, then we're going to stop, and K is going to be the minimum spanning tree of the graph. Otherwise, go to step 2. Step 2 is the case that for all edges in U, not in K, in U, which means they're not selected, if there exists an ij edge such that itself causes a cycle with existing edges in K, then we delete it. After doing this one, we find the edge in U with minimum weight, add this edge in K, and delete this edge from U. And then go to step 1 and just repeat. Let's have a look at an example, then it's going to be better. And by the way, if there is some tie in the minimum weight, we are going to randomly choose an edge, the same as what we did in the Prim's algorithm. Let's have a look at the same example here. At the same example. So in the beginning, we put K into empty set and U, I should be here. In the beginning, K is empty set, U is everything. This is just, the saddle settlement of the problem here. That's why I wrote N and A. So step number 0 is that I'm gonna set K to be the empty set and U to be the whole E edge set. And clearly, how many edges do I have? I have 1, 2, I have 1, 3, I have 2, 3, I have 2, 4, I have 2, 5, 3, 4, and then what else I have? Let me see here. Okay, 3, 5, and 4, 5. So totally, I have 8 edges. You can clearly see it. I put everything to be U, which equals to the edge set, total edge set E. Okay. Now, step number 1, optimality test. Does K include all nodes already? No, clearly not. Okay. Then step number 2 is that I'm gonna delete all edges from U that cause a cycle in K. But K is empty set here. So of course, nothing's gonna cost n cycles with K. So here I'm gonna choose the minimum weight in U, which is clearly W12. This one is the minimum weight, okay? So I'm gonna add this edge 1, 2 to K and delete this edge 1, 2 from U. Okay, and then I'm gonna have this. So 1, 2 is added to K and 1, 2 is removed from U here. There's no 1, 2 anymore. Like here, I have a 1, 2 here, but here I start with 1, 3. There's no 1, 2 anymore. And then again, go to step number 1, optimality test. Does K already include everything? I mean, every node here? No. Okay, then among all edges in U, I'm gonna delete the edge that that's gonna cause a cycle with existing edges in K. Clearly, it's impossible because, you know, for example, if I need a cycle with 1, 2, I need to have, for example, 1, 2, 2, 3, and 1, 3, right? But by adding one edge, it's impossible that you can already have a cycle here. So we're not gonna delete any thing. Let me jump here. So from this step, we're not gonna. Sorry, my fault. From this step, we're not gonna delete anything in the U set. And then the next thing is that among all edges in U, which are all these black edges, we are gonna what? We're gonna choose the one with the minimum weight and add this edge to K and remove this edge from U. So clearly here I have two choices, 2, 4 or 2, 3. Okay, so following the same step with the algorithm in the Prim's algorithm, so I choose edge 2, 4. So now what I'm gonna do is that I'm gonna add edge 2, 4 into K. I'm gonna add edge 2, 4 into K, and correspondingly remove this edge 2, 4 from U. Okay, so I'm gonna remove this. So clearly here you can see there's no 2, 4 anymore, and the 2, 4 is added here. Now my K becomes 1, 2, and 2, 4. Okay, now again, I'm gonna for all edges in U, I'm gonna delete the edge if it makes a cycle, if it causes a cycle, with edges existing in K. Clearly here, it's impossible that you're gonna add one edge and make a cycle. So again here, we're not gonna do anything here, okay? And then among edges in U, we're gonna find the minimum weight. And clearly, we're gonna choose this one. This is the smallest one left, right? Okay, so I'm gonna add edge 2, 3 into K and remove edge 2, 3 from U. So let's go to the next slide. Okay, so here we go. Now K becomes 1, 2, 2, 4, and 2, 3, and the U are the left. Let's say the remaining edges, which are 1, 3, 2, 5. Where's 2, 5? 2, 5, 3, 4, and 3, 4. 3, 5, and 3, 4, and 4, 5 here. And now what we're gonna do is again optimality test. Clearly, it doesn't include all nodes because, for example, 5 is not inside. So I'm gonna continue. However, be very, very careful here. Delete all edges from U that is gonna cause cycles in K. Be very careful here. We do have choice, we do have edges that's gonna cause the cycles. Why? For example, consider this edge, 3, 4. See it? If you add 3, 4 to K, what's gonna happen? See? I have a cycle here, 2, 4, 3. Why? Because the current existing edges in K are 1, 2, 2, 3, and 2, 4. See it? So that I cannot add edge 3, 4. See it? And very similar, I cannot add edge 1, 3 because 1, 3 is going to cause another cycle. 1, 2, 2, 3, and 1, 3. Hence, first, in step number 2, first I need to delete these two edges. Let me see, can I draw something interesting? Let's see, looks not. Okay, let me directly draw it by my hand. So let me use this color and use this. So in the very beginning, I'm gonna delete this edge, and also delete this edge. Okay, these two edges gonna be deleted. Now, among the edges left in U, I'm gonna choose the minimum weight. And clearly, you're gonna choose this one, 3, 5. 3, 5 is gonna be the minimum weight. So what I'm gonna do is that first, I'm gonna remove edges 1, 3, and remove edges remove edge 3, 4. Delete these two. So now I have 3 edges left in U, which is 2, 5. Where is 2, 5? With weight 8, 3, 5 with weight 4, and 4, 5 with weight 6. And clearly, we're going to choose the edge 3, 5 because the weight is the minimum. So now my K set becomes 1, 2, 2, 4, 2, 3, and 3, 5. And then my U set, because I'm going to choose 3, 5. I chose 3, 5 already in this step, so I'm going to remove 3, 5 as well. From let me use this notation. I'm gonna remove 3, 5 as well, from U because 3, 5 is already included in K. So finally, my U equals to 2, 5 and 4, 5. Okay, and then what we have here is that I already included all nodes in K. K includes all nodes. And again, K includes all nodes means that I already have a subgraph that connects the whole, connects all nodes, and I'm done. So finally, my minimum spanning tree of the graph is this, exactly the same as the one that we got from Prim's algorithm. Let's see here. This is the result from Prim's algorithm, and this is the result from the Kruskal's algorithm. They are the same. Okay. So again, let's have a summary of Kruskal's algorithm. First of all, I'm gonna set K equal to empty set and U equal to E, where E is the what? E is the set of the graph. Remember, we have G equal to VE. See it? Where V is the index set of nodes and E is the edge set. Here we say edge because we consider undirected graph. Okay, and then step number 1 is the optimality test, that if K includes all nodes, and of course give a connected subgraph, and then we stop, and the K is the minimum spanning tree, which we want to get. Otherwise, go to step number 2. Step number 2 is to delete edges. So for all edges ij in U, first we're gonna what? First we're gonna remove the edges that can cause a cycle with existing edges in K. So this is very important. If we can find one, then directly delete these edges from U. After it, we're gonna try to find the edge in U with minimum weight. Again, if there's a tie, just randomly choose one. Then we're gonna add this edge to K and remove this edge from U. And repeat. Repeat means go to step number 1. Okay. And then let's review this example again. Now it's gonna be more clear. I'm gonna do 2 things. number one, optimality test. Number two, deleting edges. And in number two, I'm gonna do two sub-steps as well. Sub-step number one is to delete edges that can cause cycles with existing edges in K. And step 2.2 is to find the edge in U, which means left, after removing these kind of edges. Then to find the edge in U with the minimum span, with the minimum weight, and then add this edge to K and then remove it from U. Okay, so again, here we're gonna set K initialization equal to empty set and U equal to E, and then K is empty set, so not in step 2.1 we're not gonna do anything because we cannot find any edge from U that's gonna cause cause cycles in K. Then we directly choose the smallest edge, which is 1, 2. And then again here, you cannot choose any edges in U to have a cycle with this existing edge 1, 2 in K. So we're gonna choose the minimum one. Again, here I have two choices and I'm gonna choose 2, 4, just randomly choose one, choose 2, 4. And now again, we are not gonna find any edge in U such that it's gonna be a cycle. So again, we choose the minimum one, which is 2, 3 here. However, here, yes, if we choose 1, 3 or 4, 3, we're gonna have cycles with existing edges in K, which currently are 1, 2, 2, 3, and 2, 4. So first, we're gonna in step 2, we're gonna remove edges 1, 3, and 3, 4. This is step 2.1. In step 2.2, what I'm gonna do is that after removing edges 1, 3, and 2, 4, after removing edges 1, 3, and 3, 4, I'm gonna choose the minimum weight, which finally is 3, 5. So that step 1 optimality test, yes, indeed, all nodes are already included in this graph. So I'm done. And K, which is here, this is the minimum spanning tree. Okay, which is given here. Any questions? Any questions? No question? Okay, and similar, let's do an exercise. Exactly the same graph, as the exercise left for Prim's algorithm here. But this time, please use Kruskal's algorithm to solve it and get the minimum spanning tree. And I'm gonna stop for about 2 minutes, and you are very welcome to tell me your solution. And again, it's gonna be counted as class activity and the bonus points. Everyone, please take a piece of paper and do it. Thank you. Okay. Any volunteer to solve this problem? Bonus points.
I'll go.
Okay. Who are you? Sorry, I cannot see your face.
This is Nathan.
Okay. Okay. Yes, Nathan, please. Give me 1 second. Before you do it, let me open it here. And okay, now I move it here. To make my life easier, let me copy and paste to have another graph. So because we're gonna delete many edges. Yes, Nathan, please tell me what are your steps? Hello.
Sorry, I forgot to unmute myself.
Okay. Yeah. Please tell me your steps.
So first I go from 1 to 3.
Yes. Because of what? Because it's the smallest edge, right?
Yeah.
Okay. Yes. And then what is the next one?
And then I went from 3 to 6.
Are you using Kruskal's algorithm?
I thought so.
For Kruskal's algorithm, maybe in the second step you have another choice. So among all these black edges, first of all, you are not gonna delete anything in step 2.1, right? Because nothing is gonna cause you make a cycle with edge 1, 3, right? And then what is the next? Among all these black edges, what is the smallest weight?
Oh, so they don't have to be connected?
Sorry?
They don't have to be like previously connected?
No, they don't have to. Let me show you the
like
step here. So have a look at here. This is Kruskal, right? They don't have to be connected. Here is that first in step 2.1, you're gonna remove edges that is gonna cause a cycle with existing edges in K. Then find the edge in U with minimum weight. So it doesn't matter they're connected or not. They don't have to be connected.
Okay.
You know what I mean? So you only need to find the minimum weight because you're not gonna remove anything in step 2.1. So you're gonna choose the edge with the minimum weight here, which is 4, 5, right?
Yep.
Okay, very good. Yes. Okay, then you're gonna choose 4, 5, and then what is the next one?
3, 6.
Very good. Yeah, 3, 6. And again, don't forget step 2.1, which is because there's no edge cause the cycle here. Yes, and then continue.
1, 2.
Okay. Here there's a tie, so you can either choose 1, 2 or choose 2, 5. There's no difference. Okay.
Yeah.
For example, you choose 1, 2. Very good. Yes. And then what you're gonna do?
And then you would delete 2, 3.
Very good. Okay, so this is step 2.1. Do not forget it. Okay, very good. You are gonna delete it. Let me. Which notation is the deleting? I think it's kind of like this one. Okay, so you're gonna delete 2, 3. Why? Because 2, 3 is gonna cause a cycle with edges. Let's say 1, 2, 1, 3, and 2, 3. Right? Okay. And then what you're gonna do?
And you'd go 2, 5.
Very good. Oops. Very good. Go to 2, 5. Mm-hmm.
Then you delete 2, 4.
Mm-hmm.
And 3, 5.
Yes. Give me a minute. Let me change it. 2, 4. And which one? This one. Okay. Yes.
And 5, 6.
5 and 5, 6. Yes. I didn't see it even. Thank you. Let me see. It's here. Yes. And then
5, 7.
Yes, because here you only have 2 choices, 5, 7 or 6, 7. You see it? Because all others are already deleted. And then clearly you're going to choose 5, 7 because it has the smallest weight. Yes, you are correct. Very good. Okay, so in this case, thank you very much, Nathan. So in this case, you can see the minimum spanning tree is in this way, and compared with the one we found in Prim's algorithm, see, exactly the same. Got it? So that's Kruskal's algorithm. Any questions? Any questions here? No question? Okay, now let's try something else. Because in the beginning, we selected 1, 3 first, right? And indeed, there's a tie. What if we start from 4, 5 instead of 1, 3? What's going to happen? It should give you the same answer. Let's have a look. So first, we start from 4, 5. Okay, so we choose 4, 5. And then in the next step, we're gonna choose 1, 3, right? And there's no cycle at all, okay? You see the same. And then after it, it's gonna, all results gonna be the same. For example, I'm gonna choose 3, 6. And then previously we chose 1, 2 first, right? This time let's choose, let's say 2, 5, because in the algorithm it says randomly choose 1 if there's a tie. Okay. Once we choose 2, 5, we're gonna do what? We're gonna immediately delete this one because it's gonna cause a cycle. So I'm gonna delete this one. And then what is the next one? The next one gonna be 1, 2. See it? Okay, so by choosing 1, 2, I'm gonna delete what? I'm gonna delete this one and this one, and this one and this one. These 3 edges. Let me use the same color. Okay, then the one left is of course this one. So I'm gonna choose this one. See it? So again, exactly the same answer. Okay, so this is an exercise. This is the result of the exercise here. And we've seen that they're the same. And if we have a closer look, at the Kruskal's algorithm and the Prim's algorithm, we just compare them. You're gonna see what in Prim's. Let's start from Kruskal's algorithm because we just finished it. In Kruskal's algorithm, after the optimality test, what I'm gonna do is to actually delete edges. You see it? No matter, let's say, delete from, delete because the edge itself causes a cycle with existing edges in K, or we remove it because we choose it. What we're gonna do is to delete edges and see what happened in Prim's algorithm. In Prim's algorithm, we're gonna add edges. See it here? This is a big difference. People may say that, hey, actually in Kruskal's algorithm, you also add edges. Because you're going to add edges to K, which is correct. But the main part of step number 2 here is to actually delete edges from U. Okay, 2 methods, two reasons for deleting again, either this or this. And have a look at the Prim's algorithm. Mainly what we're going to do is really to add edges to P. See it? Rather than deleting edges something, the main thing is to add edges. So there are 2 kind of like different ideas of finding the minimum spanning tree, but the results gonna be the same. Okay, so any questions about Prim's algorithm and or Kruskal's algorithm? No question? Okay, the next thing that I'm gonna introduce is the formulation for MST. Indeed, for MST, it's not so easy to formulate the problem. Let's have a look. Let me directly give you the solution, and let's have a look at why it is the truth. First of all, for a given graph G equal to VE, I assume that I have totally n nodes. This means the cardinality of V, meaning the total number of total number of elements in V equal to n, meaning I total have n nodes. So the MST can be formulated as follows in this way. Okay, so the objective function is to minimize the total weight. And xij is a binary decision variable that if edge ij is included, here we go. If edge ij is included in the MSP, then xij equals to 1. Otherwise, xij equal to 0. So it's a binary variable. Then it's very clear that you're going to have what? You're going to have objective function equal to wij summation of ij, such that summation of ij for wij xij. So if xij is really in the MSP, then its weight will be counted. Otherwise, the weight will not be counted. So this is very simple. The next one is the constraints. But the constraints here are not that not that simple. Why? Have a look at this. For example, let me check this. Have a look at this example. Here, total how many nodes do I have? I have 5 nodes, right? How many edges in the spanning tree. I connected. I have 4 edges, you see it? And then, for example, in this exercise, let me make it smaller. No, cannot make it smaller, okay. In this exercise, very similar. Let me see. My final answer is this, right? Anyway, let me use the Prim's algorithm, which is easier. Totally, how many nodes do I have? I have 7 nodes. And totally, how many edges do I have? 1, 2, 3, 4, 5, 6. 6 edges. And actually, you think a little bit, you're gonna see that they're gonna always be what? They're gonna always be n minus 1 edges included in the MST, sorry, the minimum spanning tree. Why? Think about this. Suppose you only have 2 nodes. How many edges would you have? You're gonna have 1 edge, right, in the minimum spanning tree. Okay. Now, to add 1 more node, you're gonna create 1 more edge. See it? And that's the reason why the total number of edges included in the minimum spanning tree must be n minus 1, where n is the number of total nodes included in the graph. And that's the reason why we have this constraint, that the summation of xij must be n minus 1. The most difficult constraint is this one, the second one. This tells you that for any subset of vertex v, s is not equal to v, we must have what? We must have all the edges here in this subset equals to the cardinality of the subset minus 1. What does it mean? Okay, let's have a look at here. So for example, in this graph, the v is 1, 2, 3, 4, 5, 6, 7, right? Let's randomly find a subset. And let me, for example, let's say s equal to play any subset of v. Let's say 1, 2, 3, for example. Okay. So the second constraint for this s tells you what? Tells you that the summation, then you're gonna have this. You're gonna have x 1, 2 plus x 1, 3 plus x2, 3. This is less than or equal to what? Less than or equal to 2. Why? First of all, let's have a look at the right-hand side. The cardinality of s. Here, the cardinality of s is 1, 2, 3. And 3 minus 1 equals to 2. So the right-hand side should be 2 for this specific s, okay? And then how about the left-hand side? Left-hand side tells you that for any, you're gonna sum the edges in the subset of s equal to 1, 2, 3. And for this ES means the edge composed, or the subgraph of the edges in the subgraph composed in this subset. For example, consider the subgraph here that includes edge 1, 2, 3. So your small subgraph is this kind of like a triangle, see it? So yes, indeed, edges 1, 2, 1, 3, and 2, 3, all of them are there. So you have this. But what if, for example, I don't choose this as s? I choose another s. For example, I want to play with s equal to, let's say, 1, 2, 6. Then what's going to happen? If edge equals to 1, 2, 6, then what you're going to have is, let's have a look at the right-hand side. Right-hand side is always 2. Why? Because I have 1, 2, 3. 3 s includes 3 nodes, and 3 minus 1 equals to 2. So right-hand side is still 2. But the left-hand side, in this case, you're going to have what? Erase this one. This time, you're going to have a subgraph composed by nodes 1, let me try this color. By nodes 1, 2, and also 6. See it? So in this case, you're going to, wait. Cannot continue it. So I cannot continue writing here. Come on, this is too stupid. So in this case, you're gonna have this. First, for s equal to 1, 2, and 6, you're gonna have x 1, 2 less than or equal to 2. Why? Because for 1, 2, 6, you only have one edge here. See it? Because you do not have, oops, come on, the drawing is so ugly. Okay. You do not have any edges connecting directly, what I mean, connecting nodes 1 and 2, or 1 and 6, or nodes 2 and 6. The only edge included in this subgraph is 1, 2. And so you're going to have x1, 2 is less than or equal to 2. See the point here? And then the question is, how many such s do you have? Because here, what I wrote is for any subset s, well, for any s, which is a subset of V. For example, here, you tolerate V equal to 1, 2, 3, 4, 5, 6, 7, right? Okay, let me add one thing here. V equal to, oops, 1, 2, 2, 7. Then, guys, let me ask you, how many subsets do you have? The number of subsets is how many? What is the total number of subsets? So, for example, you're gonna, first of all, for any set, the empty set is a subset of V. So first, after the empty set, how many do you have? You're actually gonna have 2 to the power of 7. You know why? Because for any node, you're gonna consider whether it's included in the subset or not. So okay, let's start with a relatively simple example. For example, suppose, okay. Suppose, for example, let's make my life easier. Suppose V equal to 1, 2, 3. So the subsets are what? Let's enumerate it. Let's say empty set, and then 1, and then 2, and then 3, and then 1, 2, and then 1, 3, and then 2, 3, and then 1, 2, 3 itself. Total how many you have? 1, 2, 3, 4, 5, 6, 7. See it? You total have, and also you have the empty set. So total you have totally 2 to the power of 3 equals to 8 subsets. And similar, if your V is 1 to 7, you're gonna totally have 1 to the power of 7 subsets, which equals to 128. So if I consider S is not equal to V, S is not equal to empty set, so I still have 126 such constraints. And that's huge, that's terrible. And you can see, suppose my V is 1 to n, then the number of subsets is 2 to the power of n, which is exponential. And in most cases, I cannot tolerate it because in your real applications, this n could be, you could have hundreds or even thousands of nodes. And the 2 to the power of hundreds or thousands, no way. You cannot explicitly, for each subset, you're gonna have a constraint. You cannot tolerate it. And that's the reason why this method theoretically, of course, is correct, but it's not that practical. Simply because this means for any S in V. And this is something really, really huge that I cannot tolerate it. And for any such subset, I'm gonna create such a constraint. And totally, I'm gonna have how many constraints? I'm gonna have 2 to the power of n such constraints. And then the question is what? The question is whether I can find an easier way. By the way, I forgot to interpret this constraint. So so first of all, small. So first of all, for the first constraint, it guarantees that the total number of edges included in the minimum spanning tree must be n minus 1. This is the meaning of the first constraint. This is very simple to understand. What does the second constraint mean? So for example, again, let's consider 1, 2, 1, 2, 3. Let's consider this. Consider S equal to 1, 2, 3, for example. So that you have x12 plus x23, 1, 3, 1, 3 plus x23 is less than or equals to 2, right? Okay, this tells you that among 1, 2, 1, 3, and 2, 3, these three edges, you must select you must select at most 2 edges. This actually prevents you from doing what? From making a cycle. See it? This tells you that, hey, there's no way you can choose all of the edges that are 1, 2, 1, 3, and 2, 3, which will give you a cycle. And clearly, for MST, there must be no cycle. Why? Because it's a tree. By the definition of a tree, it's what? It's a connected and a cyclic graph. See it? And hence, actually, the meaning of this constraint is to eliminate subtools. The subtool, what I mean here, is a subgraph of the original graph that is gonna have a cycle. So this is the meaning of this constraint. And we can play something bigger. For example, let's consider this, but it's gonna take a long time to write. Anyway, I think it's worth it. Consider S equal to what? S equal to, for example, 1, 2, 3, 5, 6, for example. So it's going to be a subgraph like this way. 1, 2, 3, 5, 6. It's going to be something like this. In this case, what do you have? You're going to have x 1, 2 plus, okay, let me start to write this way rather than make it, plus x 1, 3 plus x 2, 3 plus x 2, 5 plus x 3, 5 plus x 3, 6 plus x 6, 5. 6, 5. Did I miss anything? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, yes. Less than or equal to how many? Do you have 1, 2, 3, 4, 5? Less than or equal to 4. So this means that in all these subgraphs, in all edges included in this subgraph, you must choose at most 4 edges. Why? Because if you choose 5 edges, then there's going to be a problem. You choose 5 edges, for example, you can choose, for example, 1, 2, 2, 5, 1, 3, 3, 6, and also 6, 5. So this constraint prevent you from doing this, prevent you from making a subtool, or which gives you a cycle. So this actually helps you, and this is called a subtool elimination constraint. Okay, and the people may ask you a question. Ask me a question. People may say, hey, for example, here you say you're going to choose 4 constraints. You're going to choose at most 4, right? It could still make a cycle. For example, you can choose, let's say 1, 2, 1, 3. Let me use this color to draw it, which is easier. For example, I can choose 1, 2, 1, 3. Let's say 2, 3, and 3, 6, for example, in which a cycle is included. 1, 2, 3, right? So there's no really subtool elimination. If you just consider this constraint, yes, you are correct. However, don't forget that this is for any S in V. In other words, you have such a constraint for the subtool for the S equal to 1, 2, 3 as well. And from there, you're going to have x12 plus x23 plus x13 is less than or equal to 2, which actually prevents you from making such a selection. See it? And that's the reason why, as long as I list this as long as I list this constraint for all x as a subset of V, I must eliminate all the possibilities of subtool. And hence, this is safe. In other words, by doing this, you can really eliminate all possible subtools and guarantee that the solution given, the feasible solution given by these constraints will give you a minimum spanning tree. It will give you a spanning tree, actually. Minimum is because of here. I have the minimum weight, so it must be the minimum spanning tree. Any questions here? You do need to do some examples. I mean, after the class. The best way is, for example, have a look at this graph, or you can use the graph, which is here. Try to list all or most of their subset. So totally here, you must have what? You must have 2 to the power of 5 subsets, minus the empty set, minus the one itself. So you're gonna totally have 30 subsets. And you don't have to really list 30, but you do need to list several of them. And then try to write the corresponding the corresponding subtool elimination constraint, and see what will happen. And then you're gonna understand why it is really a subtool elimination. Okay, so this is one formulation way. Unfortunately, this is not practical because we have exponentially many, constraint of this with respect to n. So is there a method that is practical? And the truth is, of course, yes, which is some polynomial sizes of the constraints. For example, we can have MTZ constraints, or we can have list the hoop constraints. Both of them are proved to be very efficient in practical applications. Due to time constraint, and also because this is an undergrad level class, I'm not gonna introduce these two constraints in detail. Especially for the MTZ constraints, I would mention a little bit MTZ constraints. Traveling salesman problem. Where's the Wikipedia? I guess I can delete this part. Traveling salesman problem. Okay, Wikipedia. MTZ. Here we go. So this is something about the MTZ constraints. If you're interested, you're welcome to have a look at this part. Just go to Wikipedia and search traveling salesman problem. And the one part here is the MTZ constraint. The reason I want to mention it is because first, the MTZ constraint is relatively simpler to be understood. It just includes one constraint here. Where it is? It's here. Of course, if you want to include, the upper and lower bound, then it's going to be 2 constraints. And here, totally, how many constraints do I have? I have n choose 2, which is a polynomial, n squared, O(n) squared constraints. And these constraints are going to be very, very efficient, relatively simple, compared with the constraints that we mentioned here, which is exponential. See it? And here, this is polynomial. And the second reason why I want to mention it is because this page something is composed by myself. So I wrote some part here. I don't know whether this is the version that. No, I think somebody already edited somewhere, because I remember I added a very clear explanation about the meaning interpretation of the UJ UI, and I gave another set of the constraints here. Where's my version? Holy. Anyway, trust me, this is not as beautiful as the version that I edited. So actually, it does have very, very beautiful interpretations, which will greatly help you understand the MTZ constraints. And so, for this kind of formulations, the most important thing is to understand it rather than brutally memorize it. Brutally memorize this kind of constraints, it's going to be very, very tired and very, very difficult. At least for me, it's very difficult. However, if you can understand the constraints, you can create it by yourself. You don't have to memorize it. And then here's something about the general formulations for MST. By the way, the part of here, which means, for example, MTD constraints and hoop constraints are not required in this course. However, I can, in the homework or exam, I may give you a graph and then ask you to explicitly write this, to give the formulation of MST using this formula, okay? And here, be careful that this is for any S in V, meaning that you have to explicitly list all constraints. So totally looks like here I have only one constraint, but actually this constraint includes actually how many? Includes actually 2 to the power of n minus 2 constraints. And this is a big number, very, very big number. Consider, for example, n equals to 10. Then, sorry, there's something wrong. It should be this. So minus 2 is after 2 to the power of n. Consider if your n equals to 10, then this number gives you 1022. It's a very, very large number, okay? And in the homework, I probably will give you a very baby graph and to ask you really list it one by one by one. And then you're gonna feel the pain. Why this one is not that practical. But the MTZ constraint is a polynomial, which is much easier, okay? That's everything about lecture, what is this lecture? Lecture 10 or 11, this one is lecture 11. If you have any questions, please feel free to contact me by appointment, or you can visit my office hours, online office hours, of course. I do have office hours today. Actually, let's call it Zoom hours today from 4:30 to 5:30. And the same Zoom room. Okay, that's everything about today's class. Thank you very much and have a good day. Bye-bye.